more information to it. So that's what I'm trying to do, is trying to come up with a glossary for all the classes that we teach. And then later on, instead of giving out the whole thing, I'll just clip part of the glossary that relates to that class. Of course, yeah, that's what I'm trying to do. Well, I'm trying to do it relative to classes, right? Except we don't teach any computer classes, but I figured it was easier to split it out than to try to. So I'll look this over. What I've done on the Blackboard site is I've uploaded the symbol chart for the standard ISO symbols. Right. I'm having all I tried to rob a hard drive to fix my computer, but I can't find one that works. So in the reference material section, this is where you'll find the new glossary that's been updated. And of course, it's real long, guys. And like I said, I'm sorry about that. But, so there's been some new terms, and I put those on the study sheet that we talk about. And the problem we have with so I've added a section on solid state electronics because I got to teach that class next semester. And then of course computers, we've dealt with that quite a bit in it is. I'll have to sign you up. It's going to eventually have a prerequisite, but what we're trying to do is we're trying to get through. So if you've had this, I'll override it. Got fluid power in here, which that's a really good class if you're in automated manufacturing that you need to take, and then networking. I think there's some networking terms on here that we haven't dealt with. Some of y'all is having problems between a DTE and a DCE. So what's the difference between a DTE and a DCE? Yeah, that's what it is. But basically, DTEs are in what we're communicating with. So they generate the communication and they receive the communication. Everything else is just in between. Right? Does that make sense? So whatever generates the communication and whatever is intended to receive the communication, that is your DTEs. And if I connect two DTEs together using especially Ethernet, we have to use what we refer to as a crossover cable, right? Everybody understand that? DCEs, these are data communication equipment. These are your routers, your switches, your gateways. These are all considered to be DCEs. It's what the information flows through from the transmitter to whatever the intent is, right? You understand? So when you come up here and you access Lawson State's website, well, that is a DTE you're accessing. It's a web server, right? It's a computer somewhere running that application. But how many things do you go to access Lawson State's website? A lot. First of all, here you go through a wireless access point, which is basically just a switch, but it's wireless, right? You understand? From that, you go through routers. From that, you go through gateways. You go out on the internet, right? You understand? You go through DNS servers. You go through all kind of stuff just to get to where you're going. And then you finally, when it comes back, it's got to do what? It's got to come back through all that stuff. So what information flows through is what we call these data communication equipment. If we hook a DCE to a DCE, we use a straight through cable. If we use a DTE to a DCE, we use a straight through cable, right? You understand? DCEs to DCEs, DTEs to DCEs, we use straight through cables. It's only when we hook a DTE to a DTE that we've got to use a crossover cable. Does that make sense? So that means when you hook this sucker up to this is a DTE, right? You understand? This is a DTE, then what do we have to use? We have to use a crossover cable. What? Data terminal equipment. So it's the terminal, it's the end. So in electronics, we call every conductor eventually comes to an end, and we call that termination, right? You understand? So that's what it is. So my computer can generate, it generates the packets, and it receives the packets, and it does something with it, right? You understand? This thing right here generates packets, and it receives packets, but it might have to go through things, right? You understand? So I'm using a straight through cable right here because I'm connected. It came unplugged. I'm connected to my computer to a switch. So I've got a switch up here, right? And then my PLCs are using straight through cables because I'm connecting a DTE to a DCE, right? You understand that? So the switch is a DCE. Now, this is the way it's supposed to be. And that's the way it's supposed to be. Most of your switches are extremely smart because they realize people make stupid mistakes. So most of your switches now are actually computers. And they will figure out if you hooked up the wrong type of cable. So just about every time here lately, right, basically to a switch, it doesn't really make any difference. It figures out the transmit and the receive, and then it routes it electronically. But that's not the way it's supposed to be, right? You understand that? Yeah, I might be using a crossover cable up here because I know I can get by with it. So yeah, switches are real smart. They realize that people make stupid mistakes. So y'all look that over and see if y'all got any questions. Got a lot of acronyms, right? No, I was talking to Milton. Milton wants to take the level 2, Siemens level 2 exam. And what they do is they don't give it unless they have at least 10 people that takes it. Of course, what they've done for us is they've let us piggyback on top of other groups because we'll never get 10 people at one time that wants to take things. So they had one set up for, there's one little mistake I think I made when I was listening to my recordings. Let me turn on the projector. And that was IPv6. IPv4 is real easy to remember because it uses 4 words, right? 4 bytes. So that makes sense, IPv4. But you got to understand the v4 is just the 4th version of the IP standard. And this is why, even though there was an IPv1 and IPv2, it was never out on what we're dealing with now. So it doesn't make any sense for us to cover those. The 2 main versions that we have out for IPv now is IPv4, version 4. This guy right here has a 48-bit number. I'm sorry, a 32-bit number. And what they do is they subdivide it into what we call octets, because these are bytes. Each one of these represents 8 bits of a 32-bit number. And then what they do for us is they convert it to decimal, because we're not familiar with binary, and most people are not familiar with hexadecimal, but they're familiar with what? Decimal. And you got to understand, computers don't understand decimal, but they can convert it real easy, right? You understand? So that's why you'll never see any one of these guys greater than 255. You'll never see greater than 255. You ever notice that? Because that's the biggest number we can represent with 8 bits. Now, theoretically, this would give us 4,494,976,255. unique IP address. Unfortunately, the actual number is smaller because they reserve a lot of it. So they have some IPs that have special functions. And we have exhausted the IP address. I mean, even though this seems like a lot, right? You understand? How many people are in China? So they could literally use half of these, right? You understand? If everybody in China, they got like 2 billion people over there in that country. They could literally use half of these, and just think about the number of IP addresses you use. How many you use? You haven't got any to go use at your house? Huh? A lot. Your cell phone, every cell phone you have in your house uses an IP address. Every tablet you have uses your IP address. If you have a wireless router, it has an IP address. If you got a modem, if you got a smart TV, it uses IP addresses. So if you think about how many IP addresses one family in the United States uses, you understand that we've exhausted this. So what did they do? Well, they played around with, now we skipped over 5. We never saw 5. It was just in development. So now we've got IPv6. IPv6 is 128-bit binary number. So that would give us 3.4 times 10 to the 38 combinations. A number that we just can't even believe. Right, you understand? That's a big number. In fact, I think most calculators will give up on it. So it's 2 raised to the, where's my raised to that? Let's calculate right here. 128. So that's the number of IP addresses we have with IPv6. And you can start moving this over, right, in groups of 3s, and sooner or later this calculator can't display that number, it's so big, so it jumped into it's a scientific notation, right? That makes sense? So how long is this guy going to last? Yeah, we'll probably be long gone. I can't imagine. That would probably be each person in the world using 1 million IPs. So I think this is going to last. The big problem was that they couldn't do it in decimals. So what they did is they shifted over to the hexadecimal. Each one of these represents a word, right? Does that make sense? And then they normally separate it with code. Now, sometimes you'll see this last byte in a proof using the old 64, but the old 32-bit IP address. That's what they've done. Those software is they've assigned the old IP out here on the lower side. But this is normally the way we display that. So this computer, it was probably assigned an IP address. And by the way, this is called command prompt. And command prompt is this is what we used to see, by the way, when the personal computers first came out. They basically used this technique. This is the command prompt of DOS. Just about everything we do that relates directly to controlling the TCP/IP protocol suite deals with using command prompt. So if you're in networking, by George, you'll learn how to use this stuff. One of the commands we got is ipconfig, and this tells us how our thing is configured. And then we hit enter, and then this will come up, hopefully, guys. And it should tell us what's going on. They don't like it. Okay, so here's the IP configuration for this computer. And of course, this tells us this is the IPv6 address. This is the IPv4 address. This is the subnet mask. And what does the subnet mask do? So this is a class B, 10.99.11.11, what we call a class B IP address. But we basically use this subnet mask right here. What is the subnet? What does the IP address contain? It contains 2 things. So nobody knows. I think we even talked about this before. In fact, I know. So does an IP address contain? It contains two parts. Huh? It contains a network ID followed by a node ID. And your computer is considered what we call a node. So basically anything that's addressable on a network is called a node. Because a switch is not a computer. A switch is not considered a DTE, right? But it's considered to be a node. So we have a node ID. So network, and what this ability gives us the ability to do is to divide a big network up into what we call subnets. So a subnet is a division of a large network, right? You understand? That makes sense? Now what the subnet mask does is it tells us which is which. It tells us which portion of the IP address is the network ID, and it tells us which portion of the network is the addressable node ID. So ones belong to the network ID, zeros belong to the node ID. And you'll never see a zero inside the ones, and you'll never see a one inside the zeros. That makes sense? Yes or no? So if I come up here and say 10, so 10 is real easy to come up with. So here's my, oops, it's real easy to come up with, yeah, Rich. So 10, it is, I'm still doing it wrong. So this would actually be this IP address. I need to bring it back up here. What was it? 10. So somebody write 1099. I'd have to do 99. 1099 1121. So this would be 10, and then 99. Let me do it on my calculator. When I teach digital, I can do a bunch of these in my head, but a long time since I taught digital. So what I'm going to do is I'm going to put my computer into programmers, and I'm going to enter 99 in decimal, and I'm going to convert that to binary. So it's 63. What was the other one? 11? Huh? And what was the last one? Huh? 21. I'll just make up something. So this would be then I come down here and I say 255.255, and then I'm putting zeros down here. So it means this right here identifies what network this computer belongs to, and this defines the computer on that network.
So the first half is network ID, the second half is node ID?
Yeah, and your route ID would be occupied down in here. So your router only looks at those bits right in there, and it defines, okay, what route are we on. So a router you identify the route, how many routes you got. So my router at the home's only got 4 ports. So all it would use is these 2 bits right here to determine which one of those ports it goes out of. So if you looked at the IPs on my different computers, the only thing that would change would be in the network ID would be these 3. One of them would be 10, whatever it was, and then this right here. Then what I have on a class, so on a class B, I could have 16,536 computers. Technically, I could have that many computers on that route. On a class C, which is the smallest you can have, those are your 172s, 192s, all that. Those are class Cs. And those use a subnet mask of 255.255.255.0. And it'll automatically assign the subnet mask now. So the subnet mask tells us, it identifies what portion of the IP address is the network ID, and what portion of the IP is your node ID, your addressable node ID. So here we use, on our wired network, we use 172s, which is the class C. And then on our wireless network, we use 10s, which is the class B. So the college could have 65,536 computers on one of the routes. And I don't know why they decided to use a class B, but it's a private IP, right? You understand? That makes sense? So you can look up private IPs. Normally when you buy a router, it's a 192. Everybody knows that, and that's a private IP.
That's the default.
That's the default. But you don't have to use the default. You can assign it, but you can't use a legal internet IP on a private network. That makes sense. So that's why private networks. So how many networks out in the country could use 10.10.0. something? A lot, because it's a private IP. In fact, technically, if your routers wouldn't screw up, if you was totally control of your routers, you could just make up IP addresses for a private network. Now, we normally don't, because the routers they make are designed to route certain IPs, right? You understand? So I go out and buy a router at Walmart, it wouldn't route a made up route. And most of the routers you buy commercially of you are automatically class Cs. But we could probably change it to another legal class C IP, right? That makes sense. You can look, you can Google network classes, and you would see, and they would identify the class A, B, and C's. I think I might put it in the glossary, I'm not sure. So subnet mask, and that only deals with the TCP/IP protocol, and that's the only one anybody teaches anymore, even though there were originally a lot of protocol suites out there. The predominant one was IPX/XPX, which was one that was put out by Novell, and that was it. Until when they were setting up the internet, they decided to use, when they were setting up a network that would eventually become the internet, they decided to use the TCP/IP suite, and guess what? Now that's it. As far as our networks go. Now we still have Profibus, we still have DeviceNet. Those are industrial interfaces. But what we see as time goes by, more and more PLCs are going to what they call Ethernet IP, because that's the one. That's the predominant. It gives them the ability to use devices that's already out there, right? You understand? Now, normally the switches that we buy are industrial grade switches, because they have to run in a really high noise environment, right? You understand? But technically, I could hook this up to any switch, and it would still be routed, right? You understand? It would still go through. It would still go through the subnet mask and everything. Of course, if I hook this up to the college, instead of using 192, I'd have to use 175, and then I could use 175.25, right? And then our department we have our own route. So we're 175.25.80, and they leave that to us, so we can assign those IPs the way we want to. So we could literally, if we could hook this thing up to the college's network, then I could access these PLCs from my house, right? So right now we can't, because these IPs right here won't be routed. All that makes sense now? Okay, look that over, guys. Y'all need to, I'm sorry I got off whack, but I have a tendency to do that. Yeah, test is next Wednesday, so we got 2 more lab days, right? What we got today, we'll be in lab all that day, and then we got Monday, right? And then the final will be Wednesday. No, what we're gonna do on the final day, we're gonna do a lab on that day too, and that'll be converting the Festa line back to the Allen Bradley PLCs. By the way, all these Allen Bradley PLCs, guys, are identical. So you take it out and you set it over here on the floor, what's the problem? Yeah, you gotta label your PLC, guys, because if we put it in the wrong station, it's not gonna work. Even though these stations are slightly identical, if you see one of them's got the label over there, and Rich didn't label his, by the way, but I thought if everybody else labeled theirs, I wouldn't get any problem. So just get a piece of masking tape and figure out which one is actually yours and put the label on there, because at the end we're gonna. So the last lab we're gonna do, of course, is move it back over to the Allen Bradley PLCs. We might leave the Siemens, the one that I did in the first station, just so we can show and tell. And that way, and then we're going to check and make sure it works. So that'll be 2 things. And we're going to dismount the PLCs. We're going to unwire everything. We're going to take this back. Huh? Yeah. That's real easy to do. I think we've already showed you that. We'll do what we call a factory reset. It's real easy to do. Show you how to do that. And if you do a factory reset, guys, what's going to happen? Yeah, it's going to wipe everything out. So we'll do a factory reset, show you how to do that, which would be what you might need to do out there in the industry, right? You understand? Also try to show you how we'll check and see how to do what we call a firmware upgrade for the PLC too. Y'all understand what firmware is, right? Originally it was talking about information that was stored in ROM. So usually it was programs stored in ROM. So your basic operating system, so every computer has to have a basic operating system that brings it to life, right? You understand? This is kind of like your automated nervous system that you're born with. If you're not born with your automated nervous system, usually you're dead, right? So what they did to store that basic input-output system is they put it in ROM, read-only memories. Well, by George, those were built with the programs in there. So there was really no way in the world you could upgrade your firmware unless you went to the manufacturer and they sent you a new ROM and it had a socket, you'd unplug it and plug it back in. Then what they did is they came out with something called PROMs, which is programmable read-only memory. And you could have a special piece of equipment outside the information, and you literally blew, we called it burning, because what you did is you literally blew little fusible links inside the PROM to set zeros and ones. So we called it burning ROMs, and ever since then that's the same term. But the problem is these were one-shot deals. So what you could do is once you burn them, if you screwed up, you did what? Throw them away and got another one. But now what they could do, if you had a PROM programmer and you had the right PROMs, they could send you the new firmware and you could burn a new PROM and put it in there. Then they came out with what we call EPROMs. These were electrically erasable, programmable read-only memories. I've got some over there. I can show you these, and these are still in use today. These have little glass windows on them. And what you do is you expose it to high intensity ultraviolet light, and it would erase whatever you have in there. Then you could put it into a PROM programmer and reprogram the EPROM. What was nice about EPROMs is that you didn't have to throw them away. You could use them over and over again. All you'd have to do is just do what? Erase them and reprogram them. And then cover up the little glass window with an opaque label. because you could leave these things out in the sunlight and they would do what? They would erase. Then they came out with electrically erasable, programmable, read-only memories, double EEPROMs. So that means with special circuitry inside my computer, I could do what? I could erase it and do what? Reprogram it. But we still refer to that as firmware because it's not easily done. So you have to run a special application on your computer where it can do what? Upgrade the firmware. So now we can literally upgrade the firmware on these computers. My computer does it every once in a while. It comes up and says there's a new version of firmware out. And I have to let my computer, don't never turn your computer off when it's upgrading the firmware because that's its basic I/O system, right? You understand? If you lose your basic input-output system, what happens? Your computer is dead. It's just like a doctor coming out and pulling out your brain. So we call them flashing. They call them, and thank goodness, what is USB thumb drives? They're EEPROMs, double EEPROMs. That's what they are. We have solid state drives that we can get for our computers now. What are those? Those are double EEPROMs. Double EEPROMs. Electrically erasable, programmable, read-only memories. A lot of people call them flash drives, because that's what it became. Instead of burning now, we flash them. That's the term we use. Flash. You need to flash your firmware. But what it does now, it gives us the ability, if they find a little tiny bug in this thing, because what they'll do is they'll put a PLC out. They let it go through all their engineers, all these guys. They do all this thing. They put it out to a select group that plays around with them a while, and then they'll send it out to Joe Blow. And there's things that we do that they never anticipated people will do. So right now we got a little bug, right? I've been sending them that email, and if they get a bunch of email about this software crashing, then what can they do now? If it's inside the firmware of the PLC, what can they do? They can update it. If it's inside the application itself, we can update it. And that's why we have so many different versions of the software. So we're on the 14th version of Step 7. Windows 10. But now Windows 10 calls them service packs, right? So you download a new service pack, right? Or an upgrade. So Windows 7. And what's so nice about these firmware, so that's still software. Your operating system's still software, right? You understand that? Normally. But that's so double EEPROMs gives us the ability to do what? Upgrade our firmware without doing what? The BIOS, yeah, the basic input-output system. And that's the guy that boots the PLC. That's the guy that boots my computer when I turn it on. It goes in. Just about all the time, just about all these guys run up what we call a power on self-test. So that's why when you first turn your PLC on, you see the lights blinking all over the place. It's running a little self-test to make sure it's okay to use. If the red light stays on when it runs that self-test, that means it got a bad failure, right? Then it comes in and loads its operating system. Are we okay? So, any other questions on there? So I need to put post and BIOS on there. But we have two ways we can send data. We can send it synchronously, which means everything is timed with a clock. So everything inside this computer is timed with a clock. The problem with synchronous data transfer is it adds more conductors and it becomes more complex. So just about all our interfaces now are asynchronous. So this is asynchronous, which means we send it without a clock. But what we do is we send it at a precise rate. And normally what they'll do is they send information in packets. And the packet has a header. Inside that header is just a bunch of zeros and ones. And what happens is when your receiver it understands that packet and it receives those zeros and ones, and what does it do? It allows it to get in sync with the data that it's being sent. And then once it's in sync, then it just reads at a precise time. So synchronous would be, I'm up here writing stuff on the board, and everybody's got their hands up here, and every once in a while I give a beep. I go beep, and you open it up and you see what I've done, and then you close it back up. That would be synchronous. Asynchronous would mean inside your head you got an internal clock, and you open up you would open your hands up every second. And as long as I'm writing letters up here, one letter per second, then you would be what? You'd be in sync with me. So that's asynchronous. Well, what asynchronous does is it saves conductors. And conductors cost what? Money. USB is asynchronous. Ethernet is what? Asynchronous. But how do they get by with it? Well, what they do is they organize data in packets. And the first part of the packet is the header, and it sends out a bunch of zeros and ones inside that packet. And what does that let the receiver do? It gets in sync. It can get its receive clock in sync with the data clock. So asynchronous is data sent without a clock. Synchronous is data sent with a clock. What's nice about synchronous is it has the ability to be a lot faster. Oh yeah, because everything's timed, right? Everything's in sync with the clock. Yeah. You know. So inside this computer, we're talking about gigabytes per second, right? You understand? In here it's what? It's synchronous, right? But the problem is that once you get synchronous, costs so much more money to implement. We can implement it inside a computer, but once I leave the outside of the computer, you don't need to go faster than what you're communicating with. So it'd be stupid for me to send 1 billion bits a minute to a printer, and a printer can't even do what? Can't even handle that. Now we've done a lot of improvements with serial. Now we use what we call differential interface, which gives us up to extremely high speeds. Basically, about the only thing you can do on this cable, it's a Cat5 cable, is around 400, about 1 million bits per second. But you say, well, how do we do gigabit Ethernet? Well, they modulate the information. They encode it and compress it, and they send it, and then they uncompress it on the other end. So we do have gigabit Ethernet out there, but we're not sending over 100 cycles per second out the what? Out the cable. Huh? Yeah, we send packets of information, but we do have gigabit Ethernet. But you got to understand, all this has to be done with everything in the system. So I can't have gigabit Ethernet and run it through a switch that's only able to switch 10 megabits, right? You understand that? Or 100 megabits. So, but your cable companies are really working on this. And then wireless guys are really slow. Wireless, we're still way down there. So if you ever looked at your wireless, we're dealing with what? I think 5 megabits per second is the fastest that we're going right now, using wireless Ethernet. So you're connected to Spectrum, and they're advertising 100 megabits, and you bring that up and hook it up to a wireless router. So if you want real high speed coming off your service provider, you need to use wired. Right? So all my main computers at my house are wired. Yeah, hardwired into my router. If you're using nothing but wireless at your house, then right. Of course, modulation has helped a lot. Any more questions, guys? There's no defined length of an Ethernet cable. There's really no defined length. Most people say 8 feet minimum, but there's no defined length. So you notice we made these 4 feet. You know, there really no defined minimum length on an Ethernet. Huh?
I heard people say that. Before it's long, slow down.
Technically, it doesn't if you make the cables correctly, because these guys are rated at 100 megabits. Now, it won't slow down the speed, but it will attenuate the resistance of the cable will attenuate it. So that means the maximum length you're supposed to run any Ethernet cable is 100 meters, which is 330 feet, without a repeater, which would be like a switch. We can get repeaters, but that's the maximum length of the cable, 330 feet, around 330 feet. After that, it's the cable itself. Anytime we try to put a current through a cable, every wire has a resistance, right? And if you put current through resistance, what do you get? If you get current through, what do you get? That's not what kills. Heat's not what kills. So V is equal to I times R, right? You understand? Yes or no? So what happens is we have voltage, we have loss of amplitude over distance, not because of the impedance of the cable, because of the resistance of the cable. Don't understand? So that means if I try to send signals over long distances, it's not going to change the speed, but what's going to happen is the voltage will drop down enough so your computer doesn't recognize ones and zeros as your problem. And then, so it doesn't change the speed, right? Does that make sense? If the cables are made correct. Now, if people come up here and leave wires hanging out and they get it out of the twist and stuff like that, you can change what we call the characteristic impedance of the cable. These are 100 ohm cables. So at 100 megabits, if I was to try to measure what's going on in the cable at 100 megabits, this guy would represent 100 ohms, no matter the length of impedance, not resistance of impedance. Anybody that has AC should understand that. So these are 100 ohm cables. But you can't measure with an ohm meter, right? You understand? Because that's an AC opposition called impedance. And it doesn't vary with the length of the cable if you make the cable correctly. If you don't make the cable correctly, then what you do is you change the characteristic impedance of the cable, right? You understand? And you see some guys, to make it real easy to put on these connectors, they'll untwist it a long way, right? And as soon as you untwist it, what do? You didn't change the resistance of the cable, you changed the characteristic impedance of the cable. You screwed up what we call impedance matching, which is not good. So what happens on the length is it eventually if it drops too much voltage, what happens? Then the receiver can't differentiate between a 1 and a 0, and then it gets screwed up. So that would definitely reduce your speed, because what will happen is these computers are really smart and they down drop. So that means if it can't communicate at 100,000 cycles, it automatically drops down to 10, right? You understand? And then if it can't do that, it'll drop down to 5, and that means you're really doing what? You're really going really, really slow. Any more questions? Yeah, we have cable running all over the place. Now, running between buildings, we use fiber optic cables. And what's one of the big advantages of fiber optic when you go outside? Huh? Well, I could run. I had an electronic dog fence in my house, and I ran cables all through the yard, and nobody could see them because I buried them. We can bury electrical wires. We do there's some subdivisions out there that you see no telephone poles. because everything runs underground. So that's not an advantage of the big advantage of fiber. Now, fiber has the ability to communicate at extremely high speeds, but that's not what we're using here at the campus. We have something that happens in Alabama, especially near some, it's called lightning. If lightning ever hits a copper cable, you are screwed, especially a network cable. So one of the problems, one thing nice about fiber is it's immune to electromagnetic interference. Lightning don't bother it. So anytime you're going to run network cable outside, you better use what? Fiber. Yeah. So we run fiber lanes. So if you go over there and look at our switch, which is up in the box in the top, you'll see a little orange wire coming up and plugging in. That's fiber coming from AV. So they're not using it to increase speed. They're using it for what? Protect it against electromagnetic interference, lightning. Yes, it's more expensive, but what's more expensive? Blowing out all your computers. They had a lab over here, a computer lab. I don't forgot how many computers they had in it. They could not legally punch through the firewall. So what the guys did is they found an air vent. They run the network cable up the air vent across the roof of a building and down another air vent to hook up the network. They blew out the network card in every computer in that lab. And there must have been 25 network cards that they blew out. What's more expensive? Replacing computers or running fiber? So yeah, and I told them right off the bat that they were in trouble. So now there's a procedure you go through to actually put a hole through a firewall. You can put a hole through a firewall, but there's a lot of code. Y'all know what a firewall is, right? That's a wall that runs all the way from the floor all the way to the ceiling. There's no plenum gap in there or anything. Well, there's several of them inside this building and also inside a building. And what that does is it prevents fire from moving through the attic, which is where most of it get in trouble. And you can't put a hole through a firewall unless you follow code. You got to seal it up real good. So finally, they punched holes through the firewall. But originally, to prevent from doing that, what did they do? They run it across the roof of a building. So it didn't take them long to figure out. And I told them, I said,